we went there. Okay. So I gave this talk last fall. Yeah. People didn't mind it. So I don't know. Some people didn't mind it. There was a sizable portion that didn't die by the end of it. So we're going to do that. We're going to hope that no one dies. I think that we'll get there. Oh, yes, to say this out loud, the topic is elliptic curves, a spicy introduction. So, cool. So we're going to start with some basics here. So in math, this is a majorly a math kind of talk that then gets tied to security at the end, and then they'll be like, pfft. So just hold with me to the end. Also not going to get too crazy, but also ask questions. Be like, I don't know what the fuck you just said. And I'll be like, I'm sorry, let me explain that for you. So what is a group? So we're going to start with something that's called a group. It's made up of two parts, a set and an operation, right? So a set is just a collection of things, and then an operation is what you can do with those things, right? Pretty straightforward. You could think of it like those things could be numbers, right? And like an operation could be addition. You can add numbers. That makes sense, right? This operation has to be very special. So like when you use the operation, you can't just go outside of your set. So if I say my set is 1, 2, 3, 4, 5, that's all my objects that I got, and then I add 2 and 5, that's not 1, 2, 3, or 4 or 5. So that's no good, no bueno. We're just going to throw that away, not useful. It's called closure because it's closed, right? It doesn't work. People might be familiar with something called a mod, a modulus, the percent thing inside of most programming languages. That would give us some level of closure, right? Because then we're wrapping around. That's the mod action. Associativity is a fancy-ass term for that thing, which basically just says you can use parentheses. That's a thing. So associativity equals parentheses. Pretty straightforward. Identity. So what an identity is you have one thing in the set that when you use the operation with something else, it gives that something else. So like, for example, 0 is a additive identity. It's the identity for the plus operation, right? Because I can take any number and I can add 0 to it, and I'm going to get that number. I guarantee you, I bet you can't find a number that I can't do that with. Try. And that's what's called the identity. A multiplication example would be like the number 1. Any number in the world, I guarantee you this. You multiply by 1, you're going to get that number. It's a controversial thing. I'm just saying. That's how it works. And then inverses, you can kind of like somewhat tell based off the term. They're things that kind of cancel each other out in a way. What is two elements together? Give the identity when using the operation. Example, 2 and -2, right? You add those two numbers together, you get 0. And remember, 0 is the identity, okay? Yeah, so those are a bunch of examples down below. Those are fancy math-looking things. But that's just basically the stuff I've been talking about. You can also look at like fractions, right? So fractions with multiplication, those are considered a group because they meet all of the qualifications. They're closed. No matter how many times you multiply fractions together, you're not going to get like square root 2, for example. That's just not going to happen. It's not just going to, oh, darn it, got the square root 2 by accident. Like, it's just not going to happen. And by fractions, let me be clear. I'm talking about like whole numbers, integers up and below. Yeah, and the same thing works for plus with that. Also a group. So like you can add fractions all you want. Definitely not going to, again, get square root 2. It's not going to happen. You just can't find two fractions that you're going to get that. So they're like closed. Obviously, they have that associative thing. The identity for the addition is 0. Multiplication is 1. Right? For a lot of the examples I'm going to give, those work for those identities. It's not necessarily that, like, because you can have like so I'm using numbers here for these groups, but they could be anything. It could literally be like you have a snowflake, and like you rotate the snowflake, or you like reflect the snowflake, and that would be another group. I'm not going to go into that, but like it doesn't matter what the things are as long as you have these properties. So yeah, other examples are integers, right, with addition. Meets all those qualifications. Does everyone kind of somewhat have this grasp of what that is? So it's like a collection of things with an operation that has those properties to it, like integers, like the fractions. If any of you have ever seen complex numbers before, we got a thumbs up. 1 out of 30, not bad. Okay, now we're going to get into crazy things called fields. Basically same thing, except you have another operation in there. That's the defining difference between a group and a field, is that then instead of one operation, you have two. For example, addition and multiplication. Crazy, I know. Have both things. These are examples of fields. So like we take all of the fractions. You can multiply or add, like we said before, but we just talk about it in total, right? We don't need to like separate them into two separate groups. We can just call it as a field. It's cool. Same thing with complex numbers. Same thing with real numbers, right? Real numbers are just the numbers that you're used to. Complex numbers are the ones with I. Cool. And then modulus stuff on the bottom. Question? It might be. I can neither confirm nor deny the identity of the person in the meme. All right. So, yeah.
Is there something that is a group but not a field?
So by nature of the fact that like one has one operation and the other has two, I'd say no. I mean, I'd say all of them are like that, not the other thing, because one of them has two operations and one of them has one. But you do have the case where, like I said, with the rationals, where like, or the fractions, where like you can separate a field into two groups. You see what I'm saying? Are you asking, is there an example where that doesn't happen?
Yeah.
Oh, integers. So like for integers, like I said, you had a group with addition, right? Because like it met all the qualifications. But for example, with multiplication, for integers, there is no inverse for, say, 2. There's no number that's an integer that you can multiply by 2 to give you 1, right? There's a fraction, 1/2, but there's no integer that has that qualification. That's why integers with multiplication are not a group, but integers with addition are. But that's that relationship, okay? So that's mainly the difference. You have a group, one operation. You have a field, two operations. Now, what is an elliptic curve group? Okay? Now we're putting things together. We're almost there, right? So an elliptic curve group is made up of two parts. There's an equation, which will kind of look like this right here. That fancy thing. And then a field, which is the thing that we were just talking about with the two operations. This equation has a particular form to it. I wouldn't worry too much about it, other than the fact that like y is always squared and x is always cubed. That's the defining characteristic of like the highest order stuff. Oh, I say it right there. Cool. Degree of y equals 2. Degree of x equals 3. Cool. But like so. It's made up of these two parts, and how these things work together, which I don't think I talk about in the next slide. Cool. Oh, I do. So yeah, that's what defines an elliptic curve group. So when people say like, yeah, I got my ECC SSH keys, I'm all cool, I'm going to like log into this server, I'm not using any of that RSA bullshit that people are trying to push on me. You're using this math, you're using these little groups. I'm going to get into why it's a group in a second. This is a meme. I don't know if anyone gets the meme. Okay, I guess Hector gets the meme. But like besides Hector, I don't know if anyone gets the meme, but basically a little while ago, someone solved a long-standing theorem. Someone proved a long-standing theorem using elliptic curves, which was pretty cool. But it's kind of a big deal at the time. Yeah.
Is that like the same guy that points to the light?
Oh, between these two people?
Yeah.
No, so this is Andrew Wiles, and then I think this is, what's his name? It's the dude who started dealing with elliptic curve groups. I can't remember his name. I think it starts with an M, his last name. But I can't remember his name. But yeah, they are not the same individual. This one's obviously almost deep fried, this picture. But actually, the whole thing's kind of deep fried a little bit. It's a light fry, if you will. Okay, so why is it a group? You're like, Nick, you just gave me an equation and you said it was a field. I don't even half know what those are, even though you just explained them 2 minutes ago. What the fuck is this? So this is where it's like just kind of what I refer to as like a meta math, and it gets more meta as time goes on. But so we have like this. This is what an elliptic curve would look like if you could graph it. Just picture it like this, I guess, where it just has this curvature feel and it's reflective, and that's what it looks like when you graph it, if you can. So that are also in the field. Yeah. So like how you graph these points, right? So like if you think about like equations back to like algebra 1, right? When you're talking about an equation, it's all of those little xy pairs that work in the equation, right? That's what drawing it looks like. People remember that, hopefully. So if you were to do that within the field, like you have the equation and all of the numbers that you're using are in the field, then you're able to draw it like that. So like that would be a real number field, most likely. But if you are using two operations like you are here, right, to get like to a power, you're using multiplication. And to add / subtract, that's addition. Subtraction's a fallacy. Don't worry about it. Okay, so what it actually is, right, is adding by the inverse, but that's a little different. But it's two operations there, and that's why we need a field. So to get all these xy pairs, they have to fit the operation, and then we can graph it like that if you want to look at it graphically. So like I said, it was a group, right? So our set is just all these xy pairs, right? But like, what's the operation? You're wondering. You're like, I think I remember you saying there's two parts. I don't quite know for sure. The second part was the operation. We call it plus with quotation marks. And how it works is that given 2 points, you draw a line through them. And by the nature of because of the way it is, if you will, you're going to intersect somewhere else on the curve, and then you reflect. And that is what we call addition. It's a lot of steps. That's addition. Like I said, defined very differently. But because of the way that we just defined it, it's pretty obviously apparent that like we're not going to just get off the curve, right? Like we're going to draw a line through, hit it, revert it. We're not going to go off the curve, though. Like by the definition of the operation, it's just not going to happen. We're talking about like intersecting the curve and then flipping. It's always going to be a thing. I think I know what ask, I guess. Right. So when you have right. Thank you for making me clarify that. So when we go back to this slide, and I said it was made up of two parts, equation and the field, what I was saying is that when you put in like values within the field that you're working in into this equation, it will either be true or not true, right? Like for example, if these were integers and I put x equals 0, y equals 1, then I would have 1 equals -3. That's just not going to happen. Also, you can't do it with integers. But regardless, it just doesn't work. So that wouldn't be in the elliptic curve group, right? So that's where the application of the field into the thing is. But what we do on top of that, we can almost just forget about everything I've talked about up until now, because we're dealing with something meta. So we have these two things. Like I said, we draw this nice little curve, do this nice operation, and that's called addition. We have these lovely properties. like all the properties that we listed before that make it a group. So like there's the closure property, like I mentioned. The only time that you'll go off this curve is when you just, like, for example, like say we had a point right here, and or even like say we had a point here and here with the same x value, but they're reflected. If you draw a line through them, you're going to go up, and you're never going to intersect the curve. And solve that, we'll just call that infinity. That's fine. We'll just call it infinity. And we denote it with an O because math needs to be harder. So O is part of the group. In fact, it's the identity, which we'll see in a minute. So associativity, it's true. It's a valid thing. If you think this is dry, yikes. So we're not going to do that. But it's true. And then associativity, no, not associativity. Identity, like I said, we're going to just define these points at infinity as the identity. So when you add like a point with infinity, it gives the point again, right? It's the same thing as 0. It's kind of why we chose O. It would have been nicer to use 0, in my opinion, but it's O. Cool. And then inverses, because of the way that we define the identity, we're just going to say like inverses on this thing are just when their y values are just negative of each other, so they flip. And that's the only way to get the infinity, so it works out. Everything's good. It's awesome. It's a group. We have declared a group. Now, like, what the fuck do we do with it? So, like I kind of hinted at earlier, a lot of PKI systems have like the elliptic curve option for managing your keys and such. So, or for your keys and such. So where they get their security from is called the elliptic curve discrete log problem. Don't have to get into it, but it is slightly different. Well, I guess I get into it a little bit down below. Okay, we'll get back to that in a second. And this is how we do like the operation. So like this is how we can abstract it even more to make it even easier for people to do. So like if you want to zone in on like this is the definition of a field, like I did in slide 2, you can do that. Or you can go out one layer, just be like, this is the definition of the elliptic curve group. Or you can zone out one layer more and just be like, well, if I have a point P that's on that curve, and I add P to itself a bunch of times, so we'll say K times, then I have KP. Right? If I add P to itself 3 times, I have 3P. Right? P plus P plus P is 3P. That's even easier. You don't have to think about it, right? About all the shit that's going on underneath. And then we can call that Q and do a bunch of stuff. But this is actually how like a key exchange works. It's relying on that premise of like, I choose a random number, you choose a random number. We both have our random number times P, or P, I should say. And then I'm not going to get into Diffie-Hellman. Cool. So, but the main issue here is like okay, I guess we're getting into a little bit. If I say like secret, I'm like, the secret number is 13. And then I give you 13P, and I don't say 13P, it's right, it's a point. I give you a point on the curve, and I give you P, the other point that we started with. As long as the curve is large enough, you should not be able to figure that out, what K was, yeah? Small order, yeah, okay. So the question was like the semantics of like how you choose P. So like there's ways to choose P, so that way you don't run into problems, we'll say. We'll call them security problems. So yeah. So actually the size of the P is not really at fault here. It's more about like how it's used. But yeah. So yeah. Cool. So because of how difficult this is to find K, Not going to happen before the heat death of the universe on conventional computing. Then like you get all crazy security stuff going on, right? Like you can use these as keys, like these secret values that like you have one public key and one private key, and like maybe we can make the private key the K value, maybe we can make the public key the KP value. Maybe that's exactly how it works. It is. So like there's a little bit more that we share, but that's just like meta information. And there's also this fun little tidbit, which is not going to be talked about right now. I don't know if I talk about that ever. Is that like for RSA keys, they need to be 2048-bit or larger, we'll say. Probably larger. But like the equivalent, so we'll say 3072 because I have it on the slide. So you have a 3072-bit RSA key. The equivalent strength for elliptic curve keys would be 256-bit. So you get all of the punch with less of the load there. So that's pretty neato. And that goes into like what I kind of started to mention up above, that like the actual like math behind RSA and the math behind elliptic curve stuff forces the problem to be harder to solve on elliptic curves than in RSA. And that when you're dealing with crypto, security basically equals hardness of solving a problem. Like how hard is it to get to the solution of the problem? So, okay, cool. So where else is it used? I already kind of mentioned some of this, but like embedded systems, they really only use elliptic curve stuff because they have only so much memory to deal with. So those extremely large key sizes that you need for RSA are just unreasonable to like manage. So they use elliptic curve stuff. Digital signatures, I think the going digital signature right now is ECDSA. Whenever you see EC, probably in reference to elliptic curves. When I'm talking about crypto stuff, I would Google it. But like, so here we have ECDSA, elliptic curve, digital signature algorithm. Key agreement is ECDHE, which is elliptic curve, Diffie-Hellman exchange. Bilinear pairings, that talk is probably not going to happen this semester. That was really, really dry. I tried that once. Not again. And then like there is something defined called ECIES, which you'll probably only see in like a capture the flag at this point because no one fucking uses it. And it's a way to like define encryption by itself with just elliptic curve stuff, as opposed to like key agreement, which is the #1 use case for elliptic curve points. So like that's for like TLS, we'll say, right? I'm trying to talk to a web server. I need to like agree with a shared secret key in order to use AES. I'm just being very arbitrary here, but like in order to actually do the encryption between us, right? We need to agree on a secret key, yeah?
Why does like RSA use it all?
It's legacy, mostly. In addition to like, so like recently, like last year, NIST put out a document saying, the National Institute of Standards and Technology put out a document saying, if you're going to take man hours and transition from RSA keys to ECC keys, probably don't bother. Instead, try to look for post-quantum things because #quantum is coming. So, yeah, which I guess I kind of agree with, yeah.
I don't want to get too far off track. I just wanted to mention that the curve cryptography also used in homomorphic encryption by utilizing the homomorphic property of the addition points. You can make a commitment to a secret value,
Oh, okay.
but it can only be revealed line perspective. It's called a Peterson commitment. There are lots of other constructors which use the properties of elliptic curve cryptography to do cool things where you can share secrets.
Is that's for like it's semi-homomorphic? I don't think it's fully homomorphic.
Well, like if you take like 2 points, let's say you have like, B times point Q and W times point P, add those points together,
Okay, we'll talk about this afterwards. But yeah, that would probably, I don't know if I could make, so this is a slight tangent, but like homomorphic encryption, that's something you can Google or ask about. It's cool, I guess. People, never mind, I'm not going to get into it. That's a black hole. So I think I said everything. So like questions, like I said, if you can ask questions about the talk, you can ask questions about anything you want to ask questions about in crypto. That's fine. You can say like, Nick, slide 1 happened. Don't know what happened after that. But slide 1 was a thing. I remember that there's a thing called a group. And that's fine. We can talk about it another time. But yeah, any questions? You want to just yell at me? Yeah.
If one wants to start to learn how to, understand better, what are the good resources?
Cool. So
Repeat the question.
yes. So the question was about like if someone wanted to learn more about this, what resources are there available to like go and learn about it? So let's first start with like your courses, how that's going to work. So currently how it's set up is that you're going to, I imagine, all take, what's the closest thing? Discrete math, I guess. So like after discrete math, there's another course that is not part of the curriculum called number theory. That'd be helpful. But what they do instead is that in the crypto class, which I believe everyone has to take still, hopefully, at the very beginning, you're going to learn some number theory stuff, or not really the beginning. Some point during that, they're just going to be like, here's some number theory stuff. Moving on. But so like in your courses, you'll eventually get there where they'll talk about some of this. Elliptic curves in particular, that is professor dependent for the intro class. If you're really into it, again, I'm just talking about courses, then I'll move on. But the advanced crypto course, which is a grad course, is very much involved with this by Stanislaw Radzowski.
Also, department, they have abstract algebra.
Yes, so like the group theory part of this, which is a good, very large part of this, if you take abstract algebra 1, so like you can also choose your immersions, right? Imagine that has to be a thing. One of the immersions you could choose is math if you wanted to be cool. And like abstract algebra is one of the options and highly recommend if you're going to do that. So that's that. Offline sources. Yeah. So like other than just like Googling around, there's not a lot of like great resources. For books, there are good books. So like if you want a really math heavy thing and struggle through it like the hard way, then there's like Cryptography Theory and Practice, which is rough. It's read, but it's also like if you go through it, then it's great because you learn a lot. It's a read book. And then there's also the Applications of Cryptography, which is I think the blue book that the intro class uses. Is that the name of it? And who's in Intro to Crypto right now? Understanding Cryptography. I knew it was something cryptography, yeah? Yes, thank you for reminding me that. There is a no starch press book that came out like earlier that does cryptography, and I think there's an elliptic curve. I'm pretty sure there's an elliptic curve section. There's even a section, I believe, on quantum stuffs. Brief overview, yeah. So that, those are resources. Other than that, Google's your friend. Ask around. There's a few people in the RITSEC community who know about it. Yeah. Anything else? Okay. Thank you. So now